Welcome in next episode. Today we'll discuss differences, pros and cons of gas atomization and ultrasonic atomization that we use in rePOWDER. There are different methods of spraying metallic elements. The most common one is gas atomization. For the sake of today's presentation, we'll also include plasma atomization as a kind of a type of gas atomization. We'll try to expose what are the pros and cons of both methods, ultrasonic and gas, and we'll discuss where are the benefits of both methods. Usually we address ultrasonic atomization mostly for R&D, but there are also industrial applications there. We'll expose where is actual benefit of this method and how it can compete with gas atomization. Ultrasonic atomization is not a new method. It was known already in 1960s, but somehow it's lost its competition back then with gas atomization due to higher efficiency and different market requirements. To discuss differences between gas and ultrasonic atomization method, we have to start with the very physics of the process. Right now in the slide, you can see two videos. On the left, you can see typical spraying in gas atomizer. Supersonic velocity gas is spraying our melt from the top, and the powder is the droplets are created via interaction of the supersonic gas stream and the molten melt. It requires a lot of distance for the droplet to solidify. That's why those setups are usually very large. On the other hand, in the right part of the slide, you can see ultrasonic atomizer, rePOWDER in operation. There, via ultrasonic vibration, there is a gentle mist of liquid metal sprayed and created into powder. So basically you could compare those two methods into real-life examples. Gas atomizer is supersonic spray, like a power washer, while ultrasonic atomizer is a gentle mist, like a humidifier. Gentle mist of molten titanium is what we create with rePOWDER. The most important difference is scale. No matter how efficient, how large the crucibles in gas atomizers are, it requires certain scale for the material to solidify. We need large chamber to let the droplet to solidify, to cool down with very high velocity. There are several meters required for the particle to travel through inert gas at 100 meters per second and cool down to get our powder. That's why when you observe gas atomizers, usually those are setups of 2-3 stories high, and those are usually taking a lot of space in laboratory or production floor. Also, for gas atomizers, there are much larger requirements as for compressed gas. Usually when there is gas atomizer, right behind the wall there is whole facility for the compressed gas to be delivered into the spray chamber. On the other hand, you can see rePOWDER, ultrasonic atomizer by AMAZEMET. Its chamber is order of magnitude smaller than typical gas atomizer. That's why it's fit where space is of an issue, or we would like to employ it to an existing laboratory floor. Additional part is the gas requirement. Within gas atomizers, we are consuming cubic meters per second of inert gas, argon or nitrogen. Both of those could be substantial cost for the operation. While in rePOWDER, there are only several liters per minute consumed in normal operation. With rePOWDER, we can work whole day with a single standard tank as we used for welding that employs argon or nitrogen. Such tank is consumed within few seconds in typical gas atomizer. Talking about scale, it's also about ease of operation. Gas atomizers are usually large industrial facilities. Those required skilled personnel not to blow it up. We are using a lot of gas. We're using a lot of supersonic gas and explosive materials being created. And it requires a lot of skill not to harm the device itself or the personnel. On the other hand, rePOWDER is usually operated by PhD students and students. Not having high velocity gas enables us to operate safer and without risk of decompression. Initially, rePOWDER was designed as a tool for my team at Warsaw University of Technology. We thought that having this capability of spraying several different alloys a day is essential to progress with our research. And it's possible right now with the platforms of rePOWDER that we provide. Each and every day it is possible to change material, to have even several different alloys atomized. While cleaning the gas atomizer requires skill and a lot of time to clean the spray tank. There is much more space to be considered and to avoid contamination between processes and switching with different materials. Another topic is what we get out of the atomizer. In gas atomization, usually the particle size distribution is broad. We are getting both so-called fines and oversized particles, while useful cut for LPBF is just a fraction of what we are getting out of the system. I remember when I first tried to get myself a custom powder from one of the German suppliers. It was time before we started our endeavor with ultrasonic atomization, so we tried to progress with external services and get our hands on new customized alloy. But there was no warranty of what PSD I am getting out of the system. New alloy is just a one shot, one try, and we are getting what we are getting out of the gas atomizer. There is no second try with the bar that we are willing to atomize, and basically the particle size distribution in the new system is randomized. On the other hand, having rePOWDER enables R&D team to have full control over particle size distribution. There are no fines. We can avoid getting oversized particles too. So the very narrow particle size distribution and fine-tuning the frequency enables us to get exactly the powder that we're willing to use in additive or different powder metallurgy process afterwards. So if we're talking about high quality material, in my case it was high purity zirconium based system, it is possible not to invest into multi-kilogram batches with no warranty afterwards, but to start slow, batch by batch, and optimize the alloy without getting dozens of kilograms of oversized and undersized material that is not usable for our endeavors. Right now in the screen you can see typical particle size distribution for gas atomization and for ultrasonic atomization. Ultrasonic atomization, very narrow particle size distribution that we can shift with different frequencies. Gas atomization, it's much broader. The fines, so the particles below 20 micro, are usually troublesome. With very large surface of such particles, it makes the final product pyrophoric. It is not a problem for ultrasonic atomization, because very narrow particle size distribution reduces surface of the powder and reduces its pyrophoric properties. For example, there are very few gas atomizers and teams operating those willing to process, for example, magnesium, or even worse, magnesium-lithium alloys. Extremely pyrophoric, and getting fines of such particles and such systems is very troublesome. It requires a lot of skill not to blow the gas atomizer up and prevent any incident on the factory floor. While in our case, both reducing the scale and getting narrow particle size distribution prevents the self-ignition of fine powder. That's why we are routinely working with very reactive alloys, including magnesium, lithium, or rare earth elements. Imagine working with 100 kg of magnesium powder that is self-igniting when exposed to air. That is really a challenging task, while in our case, we can work with several hundred grams of magnesium that was never pyrophoric after atomization itself. Is it always a benefit to have narrow particle size distribution? Not really. There are processes where gas atomization is required to get to very fine particles. If we are willing to have powder below 20 micra, that is really hard to get those out of ultrasonic atomizers. The physics of the process virtually enables us to provide particles this small. So if there are processes, PM processes, that requires particles this small, it is better to use gas atomizer. Yet, in the very typical case, these undersized particles, those fines, are considered byproduct. Right now in the slide you can see typical SEM images of both gas atomized and ultrasonically atomized powder. On the left you can observe particle that is decorated with so-called fines, satellites. Such particles creates powder with lower flowability, and it is harder to process those in additively manufactured manner. In case of ultrasonic atomizer, there is no supersonic jet. There is no way that those two particles will collide and stick together in the atomization process. That's why it's much easier to get satellite-free particles in ultrasonic atomizer, particularly rePOWDER, than in gas atomizer. Another topic is, what is my material? What is my feedstock to be atomized? In gas atomizers, there are several different types available. If we're operating so-called Viga, we have just a crucible and we can fit there virtually anything. As long as it melts in a crucible, then it can be sprayed and atomized. Although Viga is not suitable for materials such as titanium and other refractory or very reactive systems. To get the highest quality and to get even sprayed materials such as Ti64, it is required to use AGA, which has certain limitations. One of those is what is the feedstock used for the process. We need to create a bar to get it sprayed, and creating such a bar is a challenge by itself. Another topic is material feedstock. If we're processing Viga, we can basically melt anything that fits into the crucible. But Viga has certain limitations. It's not possible to atomize titanium, zirconium, other refractory or very reactive alloys there. To process, for example, zirconium-based or titanium-based setups, we need to use AGA, electrode inert gas atomization. It requires certain form of material, in particular a bar, that is atomized within the system. Creating such a bar is challenged by itself. We need to create an alloy, we need to cast it into such a bar form that requires a separate system. That is not an issue in case of rePOWDER. There we can process basically any material form, and if we would like to have highest throughput possible, it is possible to pre-melt it and, for example, continuously cast a bar that is used as a feedstock in atomization later on. That is not a problem for rePOWDER. Having a platform capable both of arc melting, continuous casting, and atomization with ultrasounds of refractory and reactive materials, we can prepare ourselves a feedstock or new alloy within the very same setup. it is not required to precast a long bar with vacuum induction melters like it's necessary in AGA processing. To wrap it up, gas atomization and ultrasonic atomization are different methods of spraying metallic particles. Both has its pros and cons, and there are different uses. Mostly we use rePOWDER ultrasonic atomizer as an R&D device, but it can also be used for industrial applications. For example, if we are willing to spray precious metals or rhenium, refractory, high-value material, it is much easier to process it with plasma version of rePOWDER than to process it via AGA that requires certain minimum feedstock. If we are willing to have exactly a cut of particles for laser powder bed fusion or DED, it is easier to fine-tune the frequency of ultrasounds in rePOWDER system and get exactly as high yield as it takes within the fraction that is interesting for us. In case of gas atomization, we are always getting broader particle size distribution. Although, if we were willing to have particles below 20 micron, it is not possible to do it with ultrasonic atomization. Talking about several user cases and where rePOWDER ultrasonic atomizer can be used as an industrial device. It doesn't make much sense to compete with Viga. If we are to spray moderate quality powder with materials such as steel, Viga will be always more efficient. It is possible there to spray in one shot 100 kilograms or 200 kilograms of powder. There is no way for ultrasonic atomizer to compete with that. Although, if we are talking about refractory materials such as titanium, and having in mind that in ultrasonic atomizer we are getting very narrow particle size distribution within the range that we want, there, taking into account the value of material, it already makes sense. It is even more visible when we're talking about precious materials such as platinum or gold, or when we're talking about customized alloys with high value and with high burden just to create a novel composition. There, industrial use of ultrasonic atomizer already makes sense. Talking about competition of both gas and ultrasonic atomizers. Those two methods have its place in the industry. If we are to atomize several hundred kg of typical alloy and we're okay with moderate flowability, then it makes sense to use Viga. But if we have to go into refractory materials and use AGA, then considering rePOWDER and ultrasonic atomization makes sense, because we are getting much higher yield within the particle size necessary for additive manufacturing. To wrap it up, rePOWDER as an ultrasonic atomizer was created for our team at Warsaw University of Technology because we were willing to have something better fit for R&D purposes than gas atomization. For some industrial uses, ultrasonic atomization makes sense. For others, it doesn't. If we are willing to have ultrafine particles, gas atomization is better fit. Both of those methods could be complementary though. We could use rePOWDER ultrasonic atomizer as an R&D tool to pre-select materials for further industrial atomization. Thank you so very much. Next episode will compare different qualities and characteristics of ultrasonically prepared powders.